gentlemen, and I hope you'll enjoy the day. Now I'm pleased to introduce our first speaker, and that's Professor Bart Merci. Professor Bart Merci from the University of Ghent works at mechanics of flows, heat, and combustion. And he's going to tell us about the fascinating subject of what CFD simulations can do to determine smoke dissemination in the event of fires. I'm pleased to give the floor to Professor Bart Merci.
Dank u wel.
Thank you very much for this wonderful introduction.
To the non-native Dutch-speaking persons, I will speak in Dutch because the majority here in the audience is Dutch-speaking. Vervolgens wil ik mij verontschuldigen bij de Nederlanders, want ik kom uit België.
Now I apologize to the people speaking Dutch because I'm from Belgium and I speak Flemish. Anyway, so that'll be a challenge to the interpreters. I hope everybody can hear me. I'm pleased to be the first speaker here today. Everybody is awake. I'd like to tell you a bit more about computer computation, CFD, because that is what we will be focusing on. That's what it says here, is we'll be focusing on that in the presentation. But I would like to give you some idea of how to use computer calculations in fire safety, not only on the level of science, but also designs and fire safety in that respect. What is it that we're going to talk about? First of all, I will set the scene a bit and tell you a bit more about the abbreviations, ACR, RCR. I'll be talking about that later on. I'll explain it to you. And then I'd like to distinguish between the use of computer calculations in the context of the design of fire safety systems, on the other hand, the field of scientific research. I think there's some nuances here that I would like to highlight. And then, in between, I'll give you a brief example of how CFD can be used in the context of fire safety in parking garages. And I'd like to talk to you a bit more about a new topic that we are trying to specialize in, and that is in the prediction of fire. And, of course, I will make some closing remarks. What is it that I will not discuss? I shall not discuss the review of the current state of the art, nor will I attempt to explain the assessment of quality of computer simulations. Furthermore, I'm going to make things easy for myself. I'm not going to talk about complicated issues such as pyrolysis, modeling, and interaction of water with smoke fire. But before you think that this will be the briefest presentation ever, I shall tell you what I am going to talk about. So I will be essentially talking about the gas phase. I will be talking about smoke movement and anything and everything connected with that. All right, let's not lose too much time, and let's get you acquainted with a number of abbreviations. ACR, RCR. That's more or less inspired on the A-set, R-set principle with human beings, available and required. And we have something comparable when we're talking about computing. Namely, you have something that is available. I will call it ACR, available computing resources. This is what you can use for computation. But you should also ask yourself your question, what is it that we need in order to be able to carry out a reliable computation? And this is the required computing resources. Now, important question that arises here is whether what is available is appropriate. If we have too much, how do we deal with that? I'd like to just dwell on that This is a principle, a graph of principle. It is not a scientific graph, but I want to show you a graph nonetheless. On the vertical axis, you will find what you need in terms of computing power. Computing power to make a computer calculation. And arbitrarily, at a certain level, I have a dotted line with what we have available. This dotted line is not fixed. The dotted line continuously increases. Why is that? That is because the hardware manufacturers are good to us, because computers are becoming powerful, more powerful day by day. And there's no indication that this development in terms of hardware should come to a grinding halt. And furthermore, the software developers are also providing us with more efficient computation or calculation algorithms, the faster, etc. And all these elements put together make sure that every day we have more computer power available. Whether we deploy it, whether we use it, is something else. But in essence, we do have these very beneficial and favorable factors. On this axis, we have complexity, accuracy, and modeling dimensionality. So that is the complexity of the models that you use in your computer calculation. Complexity can be in the field of geometry. If you have a very complex building, the situation is quite different than when you are assessing a simple building for a fire scenario. But also in terms of the fire scenario itself, it can be very complex. For instance, a scenario in which sprinklers are activated or not, and that obviously will have an impact on what you need in terms of computing power to do the calculation. By and large, if complexity increases, well, you will need more computer power. You see this here, this dotted line. Once again, it gives an arbitrary indication that there is a nonlinear increase of the computer power required. And there can even be a little jump here, a little increase. And that could be a sprinkler that is activated. All of a sudden, the required computation power of the computer required will increase. Now, accuracy. Accuracy mainly concerns the fineness of the computation mesh. So a number of volumes are determined, and the more volumes you consider in a certain geometry, the more accurate the results will be, and the longer computation will take, and the more computer power that you will need. Complexity of the model. An example, for instance, radiation. You have radiation heat. You can try to model it rather simply by introducing an assumption that a certain fraction of the heat release rate of the fire will be radiated, but you can also make very detailed radiation computation with soot modeling, with all sorts of aspects of gases and things. So you can go really, really far in terms of modeling. As I said, arbitrary indication. So if you add them all up, you get a certain end level of what you need in order to make a reliable computation. Now, the question is, are we sure that at a certain point in time, the available computer power is sufficient in order to consider the problem that we would like to solve? Now, a different way of depicting things, I'm not going to dwell on this too long, is, for instance, if you have complexity on one axis and accuracy and modeling dimensionality on the other axis, you will see that somewhere you'll have to take a decision, decide between complexity, geometry, and scenario, on the other hand, what you can invest in accuracy and in modeling dimensionality. So somewhere there's a trade-off, a decision that you need to make in your calculations. And when you increase towards the right in the graph, you will need more computer power. So this is more or less the situation we're dealing with. And one of the questions that arises is whether the available computer power can be equal to or even exceed what we need. Just a minor example, just to give you a broad idea of where we stand in the context of the fire safety systems design. If as a user you define a certain fire scenario and as a user you impose establish the production of soot relative to the radiative loss fraction, you see that the CFD calculations at this point in time for smoke dynamics are very feasible, very reliable as well. That is, as long as we don't touch the subject of toxicity, because toxicity continues to be a very difficult problem to solve, particularly the production of carbon monoxide. It's not a problem that is easy to solve. And geometry can't be too complex because usually with the common geometries, it's easy to do the calculations. The question is whether you have enough power available in order to deal with the details of the geometry. So with the current state-of-the-art models, CFD has a potential to generate accurate results for smoke dynamics given the fire dynamics. So in this respect, CFD can be a very useful instrument and tool to make a design. Now, that doesn't mean that zone modeling should be ruled out. I think there still is a substantial market for zone modeling, and I shall be discussing it later on in the context of forecasting fires. But also in the context of designing, these models can be a useful addition to CFD. For instance, you could decide to do a sensitivity study first with these models and then have one scenario calculated with CFD, but you could, for instance, also split a certain geography, a subway network, for instance. A certain station you want to calculate a fire scenario with CFD, but the adjacent subway tunnels and other stations, you may want to approach them with simple zone modeling in order to make CFD possible in this one station. In any case, we have to deal with the fact that the user, in the context of fire safety system design, will have to specify the fire when starting calculations. I don't think it's useful to try to calculate a developing fire from the very beginning in the context of design, for the very simple reason that a design serves to ensure fire safety for a building that has not been finished yet. It's impossible to know what exactly will happen if there's a fire, what the fire conditions will be, what the weather conditions will be. So for the time being, we will have to use user-defined fire. So the calculator will decide beforehand which fire design will be calculated. Now, if we do that, we can interpret the fire scenario itself as a prerequisite or a parameter, in the calculation. So what you get is that these calculations at this point in time are very reliable in terms of smoke concentration, i.e., if you accept beforehand that there's a certain production of soot given a certain combustion capacity. I'm not saying it's a very good assumption, but it is an assumption that is being made quite often. So if you do that, we can count on CFD in the systems design. Why would I venture to say this? Because a couple of years ago, and some of you will have seen this in Ghent, a couple of years ago, we carried out a study into fire safety in parking garages, particularly in the ventilation of these parking garages. And we did this with a fire seat that had been predefined. And we also set fire to vehicles, but well, that's something else. We have a well-controlled liquid fire with a pump that gave us a certain power, so we knew exactly what the heat was of the fire, so we didn't have too many uncertainties here. And we set it up here. You see the picture on the right-hand side. You see the diagram in a parking garage of about 30 by 30 meters and 2.6 meters height. What we did is we we regulated the extraction fans, how much smoke we extracted per time unit, and also the inlet. So here, this picture, the inlet is entirely open. It's over here. And we could also close it in part. So that way we could look at flow patterns in the parking garage. And we did a number of experiments, more than 100 to be precise, and more than 500 CFD calculations. So I think that we can safely say that we've done a thorough job. I don't have the time, unfortunately, to share a scientific analysis with you. For those of you who are interested, you will find the articles in the Fire Safety Journal of last year. It's been peer-reviewed. In other words, these experiments are correct, or to a certain extent. And to give you some flavor of what we did, and here for the CFD calculation for all these configurations, you have O's are opens and X's is closed, and this is partially open and partially closed, and these are two other configurations that we used. On the graph you see the speeds. If everything is open for the same extraction, you see that the speed is rather low, and you see the scale here on the right-hand side. 0 is somewhere over here. In the light blue, light green area, you see low speed, and the yellow arrows are pointing upwards. And if we close this for 80%, obviously you have a higher speed centrally, and you also see that you have recirculation in the parking garage. And we also determined this in our full-scale experiments. I'm showing you this to point out that CFD calculations on the one hand and observations coincided. And we did this for several flow patterns, and the combustion itself will have an impact on the flow pattern in the parking garage. So that's a bit of good news in between. Just to point out that with the current state of play, the current modulation and computer power, we are capable, given a certain fire, to have some idea of flow patterns and smoke dynamics. Once again, we had no sprinklers here, so this is a complication that we didn't study. So this is something that I'm sure we will have to study in further detail. But, and the but is very important in this good news story, we've been very cautious in determining our computational mesh. Now, we have taken our time that we don't always have, and we also invested in computer power in order to be able to do this. Because we did this calculation with FDS, Fire Dynamic Simulator, I'm sure you know it. This is a package that was developed in NIST in the US. Why am I saying this? Because turbulation in this computation package is calculated based on LES. It's an acronym, which means that the largest turbulation, eddy is a word for a turbulation in English, or simulated or followed. Now, if you want to do this, if you want to follow these swirls, your computational mesh has to be fine enough in order to follow it. So we determined that, if we check literature, and also scientific literature, by the way, that if we look at the computational mesh and we compare it with comparable computations in combustion processes, we see that our work is less fine, 1 or 2 orders less fine than we should. And why is that? Not because we are dumb, but it's because there's so much pressure, time and money pressure. In other words, it is safe to say that it's possible. What we are applying, ACR, A stands for Applied Computing Resources, so the ACR can be smaller than what we need, the required computing resources. Now, how serious is this? How much of a drawback is this? How reliable will these results be if we're in such a situation have we identified the trends, and what are the safety margins that we need to apply to our computational results? An important handicap here in terms of fire safety is that the proof of the pudding is in the eating, as they say in English. But in fire safety, it's not in the eating, because very often we don't know exactly whether a design, in hindsight, turns out to be a good design, for the very simple reason that many designs are never actually tested because there's never a fire in that building. And if there's a fire, things may have changed, the design may have been changed, or the system hasn't been sufficiently maintained. There are always reasons why, in the case of failure, a design didn't perform as we had expected. Could have been that the fire was much more forceful, much more powerful than we had expected in our computations. And that's a handicap, because that means that it takes time to learn from our mistakes. Could very well be that we've made mistakes, but we wouldn't know that, and we find it very difficult to assess that by experience. It's a given. Means that we have to be extra cautious when we interpret computer computation, which means that we need research in this respect. And this is also why we would like to start with an initiative, and I'll be discussing this later on, namely, we will be trying to define a number of benchmarks to hopefully get a better understanding of this problem that we have between ACR and RCR. And this brings us to the field of fire safety science research. Let me see where I am. Okay, so this is the field, and this idea of benchmarking is not novel, quite the contrary. A lot is being done in this respect already. A big effort is being made by the developers of FDS itself. FDS, Fire Dynamic Simulator, FDS has an extensive verification and validation guide, which is also available to each and every one of us. And when I made the presentation, there were 44 sets of experiments in it. May have changed now, and more than 5,000 data points. So where you can actually make a comparison with what you get from your computation and what has been included in terms of experiments. And the most important goal here is to make sure that FDS become more fail-safe, which is a good thing, and that is they're doing this by making it available. So if the code becomes more fail-safe, it's a good thing if a less experienced user wants to use that code. So it's a very good idea, a noble idea. On the other hand, if you look at the blog that is connected to this, the relevant blog, you see that the response of all of us as a community vis-a-vis this effort is referred to as disappointing. There's very little input. There's very little input from the academic world, so mea culpa here. And the reason is that there's really no encouragement to take part in this. It's useful work, but it's time-consuming work. It's difficult work. So it's an important effort, but we often don't take the trouble. It's a good initiative, very laudable, but for now it really is an effort taken by just the FDS people. And only recently, this was 2006, 2007, there was a new initiative that came up, and once again this was an initiative taken in the US. FM Global took this initiative, and they're developing another CFD code, and this is Firephone, and this is a sister system of OpenPhone. OpenPhone is a sort of open source CFD code that is becoming very popular in the academic world. before you start taking notes and of Firephone. Now, the effort required to use Firephone is immense. In FDS, you could even say, okay, within a week, if your experience is CFD week, you can start within a week. In Firephone, it has taken us, and I'm not going to be very modest here, but we have been working with CFD for quite a while, but it took about half a year for us to get to understand the code. So that's a drawback if it takes so much time. But it has an advantage as well, because not just anyone will be using that code. Well, anyway, these people are aware of that, and they have developed a series of workshops about the development of knowledge, know-how on fires, but it's all focused on the Firephone code. So that's open source, and a big difference with the FDS effort is that here people effectively meet. They gather together in order to brainstorm on these matters for a couple of days. Okay. We have also taken an initiative, and this under the umbrella of the International Association for Fire Safety Science. And we, being myself, but also Arnaud Trouvert, the University of Maryland, and José Truvero, who is working for the University of Queensland as we speak. Now, together we're going to initiate a series of workshops which we have called MAC-FP, Measurement and Computation of Fire Phenomena. And shortly, in May 2015, we will be holding the last preparatory meeting, and then we'll be holding the first workshop in 2017. Now, that seems a long way away, but it is has been chosen on purpose because it coincides with the annual IFSS symposium. That's why we want to organize this first workshop. And one of the things that we would like to study in depth is to quantify reliability, accuracy of CFD computation, particularly, and the models that we use nowadays with all the numerical operation and the operations of computational meshes, and the situation with experiments, etc. We will be defining a number of test cases. They may already exist. We may have to develop them ourselves. This has not been decided yet. That doesn't mean to say that the rest will no longer be relevant. Quite the contrary. No. It's very important to carry out small-scale experiments, but also full-scale experiments, but because particularly the full-scale experiments, and I would like to highlight their importance because they cost a lot of money, but they're extremely important in order to be able to analyze what is going wrong with the current computations, if anything goes wrong. So there are differences between the computations and the actual fires. Defining a crash is a bad convergence between a computation and an experiment. Why is that so important? I'm going to repeat it again because we are dealing with specific situations and we are learning very, very slowly from experience. I'm looking at the time. It doesn't look that bad. Okay, I would just like to spend another 10 minutes on predicting fire. Fire forecasting is a relatively new domain. It's been inspired on weather forecasting. Now, we all know, particularly here, but also in Belgium, and let me speak for Belgium, weather forecasts are not the most reliable forecasts if you're talking about a forecast of 3-4 days ahead. But usually the forecasts for the next day are rather reliable. Now, why are they not reliable as from 3-4 days away? Well, that mainly has got to do with the fact that we're dealing with turbulence in the atmosphere and there are jet streams and so on. But it mainly has to do with turbulence. Turbulence is something that is very difficult to forecast. You can only approach it statistically, but with our current computational power, we can make a reasonable forecast for a useful period of time. Very often it's useful to know what kind of weather it'll be tomorrow, or that we don't know what the weather will be in a week's time. Well, that's something we can live with. we could try to set up something comparable with a developing fire, particularly in view of fire response. It may be very useful on your way to the location to get information as to how the fire is developing. That you don't know what the fire is going to look like in 3 hours' time isn't such a bad thing. If you do know what the fire will be like in the next 5 minutes, that could be very useful information. It could mean the difference between entering a location or not. So that is the fundamental idea. So what is it that we need for that? We have to calculate faster than reality. It's useless to make a prediction or forecast of something that has already happened. So there's a need for speed, so to say. And that means with the current state of play, in view of available computer power, that CFD is just not possible to use because it just takes too much time to make these calculations in such a short period of time. So that means that we have to fall back on the use of zone models. Press the wrong button. Zone modeling is much faster. They don't have to calculate an impulse comparison. You don't need millions of computational meshes. You can have 2 or 3 zones, depending on the geometry, but it gives you results much quicker. So it's much better to do a number of zone model computations, and you know that you'll be working with a limited number of zones, than to do a poor CFD, because you could very naively say, okay, we're going to do a CFD calculation on a very gross or rough computational mesh. It's not a good thing, because you need to calculate very accurately. So, in this context, it would be preferable to look at zone modeling. But zone modeling also has drawbacks, because you're using very few zones. So on the one hand, you have very little information, but on the other hand, you have quite a lot of underlying modeling that it will be calculated differently automatically in CFD. Let me just give you a simple example. You have a fire seat in a zone model. Implicitly, it is assumed that it is right in the middle of the space, and then there'll be air from different directions. But if all of a sudden your fire is right next to the wall, the inflow of air will be different than what you assumed in the zone model. Now, it's a problem if you don't correct for that, because within the context of a forecast of a fire, it gives you unreliable computational results. So the idea is to make sure that the uncertainties in the parameters, you can avoid them by focusing on the data of the fire itself. One of the ideas that we started with was using CCTV, because in many complex buildings you have CCTV, and if you can point the cameras to the area where the fire is located, that could give you very useful information, which could then be used as input for the zone modeling calculation. So you're looking at what's happening, and you use that information to constantly update your forecast. That is the general principle. In other words, you use the sensor data in order, on the fly, during the calculations themselves. That doesn't mean to say that we shouldn't start with a fire to be defined by the user himself, and the situation will constantly be updated based on the data that we get. And this is an essential difference with what I said about using computer calculations in the context of designs of systems, because right now we are dealing with the situation of fire. So we feel that the most important parameter that we need is the heat release rate in combination with the thermal parameters, how much heat is leaving the location, and ventilation parameters. Are the doors open, closed? Is someone opening a door? Is there a window open? And you can introduce that in the zone modeling. These are tests that we did 2 years ago in Ghent. An apartment block was going to be demolished. It's still there, but it is going to be demolished. That's what they keep saying. Anyway, so there we did a number of fire experiments with what we say is a medium complex combustion. We have two sofas facing each other in an apartment. You may not be able to see it very well here, but what you have here is a cupboard, an open cupboard filled with paper. And by the way, you see the measurement equipment here. We say it's medium complex because there's a certain realism here. At the same time, it's not a fully furnished apartment. We did this on purpose because we wanted to see to which extent in such a situation we would be able to follow the development of the fire and also forecast it without too many uncertainties in terms of the fuel, have a certain realism in the situation. This is the day of the fire. There's quite a bit of wind. The fire's here. This is single glass pane. But the pane was held in place by the wind, just to tell you that it could just as well have been different. During the fire, as you know, the glass could have crashed. And this is the combustion. The sofa is ignited here in the corner. So here you see that the fire is developing here, and there's a full fire at a certain point in time in the area with the sofas, and this gives you an impression of smoke in the door opening. I'm just going to go through this very, very quickly because the chairman has just pointed out that it's time for me to shut up. So this is the layout. This is the apartment with the sofas, the cupboard, and this is the adjacent room, and then the corridor, a number of cameras, and also the measurement equipment. And we use the results in different ways. And this is in cooperation with iMinds, an institute located in Ghent, and the Faculty of Electronics is part of that. And they have provided us with automatic quantification of the fire during the development of the fire. So this is what we see here is what we can see through the cameras, but it would take too long for someone to watch that and start computation or calculation. We don't have time for that when a fire starts. So we have to get automatic data from the flames and use that to introduce it in our calculations. Logarithms were developed by Stephen Verstockten, starting with this visual. He calculated certain volumes, and from there on he calculated the extension of the flames of the sofas and also the direction, the longitudinal direction, forward direction. And you can use that in zone modeling because you can input the size of the fire immediately. And you can do something similar for the smoke, the height of the smoke. I'm going to skip that, and you can also compare that to other measurements. So I'm not going to dwell on this too long. But quite apart from data during the fire, you can also try to carry out the calculation in a different way. We did this. We ignited the sofa again and measured what the heat release rate was. Here you see one of these experiments, and you can use this as input in zone modeling, but also in CFD calculation. This is an example of an input in FDS, and these are the measurement data from the laboratory, but also from the analysis of the video. And you can use that as an input for the CFD. It's not a forecast. I understand that. I realize that. Nonetheless, we try to do it with the help of zone models. And this is what it looks like. What you have is what we call a data assimilation window, which means that during a certain period of time, you look at the fire and you store the data. This is what they do in weather forecasting. You just update the data of the past few days and you do a forecast on that basis. This is what we're doing here, but the scales are entirely different. And in the weather, we look at days and hundreds of kilometers. Here, we're talking about seconds and minutes and just a couple of meters. So what we did here is for 25 seconds, we watched the fire. From there on, we made a forecast. And of course, you can say, OK, I'm going to stop watching the fire. And then you just sort of see a parabolic increase here. But nobody is telling you not to watch the fire. So the longer you watch the fire, the bigger the window will get. And this led to this rather simple configuration, but we've been able to establish forecast times of 2 minutes. So for 1 minute, in 1 minute we could forecast the development of the fire. But we're in an embryonic stage right now, but it's something we've started with. Okay, so this brings me to the end of the presentation, and allow me to just summarize. The CFD simulations can be a big help in the context of calculation of fire safety systems, designs calculations, but also to understand fire safety. And also in terms of science and scientific studies, CFD is really helping us because it's helping us to understand fires better. And in the longer term, we can perhaps also use it in fire forecasting, even though zone models would be more appropriate. But of course, they have to be carried out in the correct manner, which is not easy. As I said, allow me to repeat, I only talked about gas phase phenomena, but there's still a lot to be done in modeling pyrolysis, interaction of water with flames and smoke and fire suppression. That is, of course, to be introduced in computer calculations. And I've tried to talk about the available computing resources. And this is something we really have to map very accurately, because at this point in time, we don't know exactly what it is that we need. We do know what we're using, but what we need exactly in order to make a very reliable calculation, and that hasn't been identified very well yet. And what the implications are of using insufficient resources is also something we need to look into. So what can we improve? Well, we can import knowledge from other domains, and then we can focus on scientific aspects that are fire-related, and we very much believe in a benchmark study and in sensor-assisted fire forecasting simulation by using measurement data during the development of the fire. Let me close with a word of thanks. Thanks to all my current and past colleagues. Of course, I didn't do this on my own. I did this with the help of colleagues and also with the help of resources. So thanks to current and former sponsors. Thank you very much. Thank you very much to you also for listening to me.
Thank you. Thank you very much. Are there any questions from the audience to Mr. Mercier? You can ask them now, or you could ask them later if you prefer. Apparently, everybody was very impressed. I do have a question because you used the word disillusioning. I didn't experience your speech as such. I didn't want to. I don't want to inhibit you because there's an awful lot more I'd like to know. But I was triggered by your remark: the proof of the pudding is not in the eating, and we apparently have a systematic lack of opportunities to test fire models in practice. So that requires more experiments to do that. Large experiments are very costly. Are there any plans to launch that in a more European context? It's a very relevant and interesting question. As far as I know, there are no pending initiatives, nor are there any scheduled for the near future. But I think that one field that we're not operating in sufficiently is the real world. I'm speaking again on behalf of Belgium, but I think it holds true for much of Europe that relatively few statistical data are being collected on fires, and there are various reasons for that. I can certainly understand all of them. But as a fire safety engineering community, we would benefit greatly from doing far more about fires that took place in real life, whether or not the fire department was involved. We need to identify them, and sometimes it's difficult to understand the correct fire release. But nowadays we know far too little about what's actually happening in the world. The UK is trying to do that, so are the Scandinavian countries, and of course the USA. But generally little use is made of what really is happening in practice. So I think there's a lot to be gained there that we're now leaving unused. Perhaps that would be a challenge following your lecture, to invest more to ensure a meeting of the minds there, exchanging experiences and funding large common experiments. And your lecture will certainly be conducive to that end. Thank you.